Alright, in this video I'm going to go through that gravimetric analysis lab-based question that I talked to you about in class. We'll do the 2004 and then I'm also going to pull the 2008 lab question as well. So first of all, don't make this more complicated than it is. Essentially, gravimetric analysis, gravity just means mass. I know, gravity, weight, but we're talking about using mass measurements. That's it. That's the main idea. And really, essentially, gravimetric analysis is nothing but using the law of conservation of mass and stoichiometry. That's all it is, okay? So I'm going to walk you through some problems here. We'll do a couple of these, and hopefully you'll feel a lot more comfortable about it. Yeah, we don't need no light. All right, so number one, a student is given the task of determining the iodide content in a tablet, so it's maybe something they buy from the store, and an inert water-soluble sugar as a filler. So this tablet's got some K in it, some I in it, and it's got some filler in it. A tablet is dissolved in 50 ml of water, and an excess, anytime you see information like that, that's important, excess 0.2 molar lead 2 nitrate is added to the solution. A yellow precipitate forms, which is then filtered, washed, and dried. Hang on to that. We're going to see how that's important later. The data from the experiment are shown on the table. So we can see here we have the initial mass of the tablet, a piece of filter paper, and then we have the mass of the filter paper with precipitate. So this is post-filtering, and then we did it again, and then a third time. All right. Alright, so for the chemical reaction that occurs right when the precipitate forms, write a balanced net ionic equation for the reaction. Alright, so I'm going to go to the paper here. We've got, see, this is part A, number 1. So we're going to be reacting potassium iodide plus lead 2 nitrate, and we're just going to do a double replacement. And you're going to get potassium nitrate, which is aqueous, and then we're going to get PbI2, which I hope you identify as the solid. So remember our spectators, we got a balance, 2. So our spectators are just going to get rid of anything that doesn't change, and it's going to leave us everything that contributes to the making of the precipitate here. So PbI2 stays, and then we're going to have 2 iodides and a lead 2. So there's your net ionic. Alright, so reading on your paper here, part 2, explain why the reaction is best represented by net ionic. Alright, so I want to make this video a little faster, so I'm just going to kind of say here, only shows change. So a net ionic just shows what actually undergoes a change. The spectators don't do anything, so you don't have to include them in the chemical reaction. Alright, so part B, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. So you'll notice we did first, second, third. And again, I'm going to try to keep this as fast and succinct here. So we want to make sure all H2O is gone from drying it. Okay, when we get to the end here, we see the mass is not really changing past that last decimal place. Remember, the last decimal place is always a guess anyway. So this shows consistency. Notice a big change after the first, the second, but after the third drying, it stayed the same. So that means we're done. It's dry. Part C, in the filtrate solution, is potassium greater than, less than, or equal to nitrate? Well, if we go back to our problem statement here, I underlined excess when I read it. Excess nitrate. So we know then that from our reaction, potassium is limiting. You can even say that, limiting and excess. Alright, I'm not, the purpose of this video is not really these parts here. I'm trying to get down to the gravimetric analysis, and that's going to start here with part D. So calculate the number of moles of precipitate that is produced in the experiment. Moles of precipitate. All right. So how do we get the moles of precipitate? Well, the gravimetric analysis is not going to give you moles. It's going to give you mass. That's what gravimetric means. So the precipitate is going to be added to the original paper, which was 1.462 grams. So we could use either of these masses. I have a bad habit of always just using the last one. So what I want to do is take that last mass of the paper plus the precipitate after third drying, and I'm going to subtract from that the second line there, 1.462 grams, which was the mass of just the paper. So this is paper plus precipitate, and this is just paper. So that we subtract that, we get just the mass of the precipitate, which is PbI2. Now, I didn't ask for mass, it asked for moles, so that just means we need to do a mole conversion here. 0.236 grams, 1 mole, let's see, I did this one already, 461.0, and so that comes out to be 0.000512 moles of PbI2. And you could put that into scientific notation if you want it. Remember that your lab questions will be sig fig questions, so I did keep up 3 sig figs here, 3 sig figs here. That's 1 point. All right, and then part E, calculate the mass percent of iodide. All right, so now we're going to be using the stoichiometric aspect here of gravimetric analysis. We have found the moles of lead-2 iodide. And I want to go back now from the precipitate, because that's the precipitate. We're going to go all the way back to this tablet, okay, which is just Ki. So I know from the reaction here that my K is limiting. So the original Ki in the tablet was also limiting. The iodide was limiting. And by adding excess lead-2 nitrate, I drove all of the iodide out of solution. So what I'm going to do here is just use some stoichiometry, and I'm going to convert moles of PbI2 into just moles, PbI2, convert that just into moles of iodide. All right, so that's a 2-to-1 ratio. I'm basically just ignoring the lead at this point. Moles of iodide. Now, all of this iodide came from that tablet. So if we can just convert all that into grams, and the molar mass of iodine, 126.91. And the reason I'm using more decimals in my molar mass than normal is I don't really want my molar mass to be my sig fig limiter in these problems. So 0.130 grams of iodide is what I calculated. So from that tablet, let me write this down, and we'll bring the paper back out and look at it. The original tablet had a mass of 0.425 grams. Remember, it's got some filler in it too. And so we just used stoichiometry to figure out of this entire mass of lead-2 iodide, all the iodide came from the tablet. So we just found out how many moles of iodide that was and converted it to grams. And so to 100% here, 30.6% iodide. That's how much was in the tablet. And then in part F, in another trial, the student dissolves a tablet in 55 mils of water instead of 50. So that goes back to like really early in the problem statement. Basically, what difference does that make? And the answer is no difference. And it asks you to justify it, and you can come up with a lot of things here, but I just keep it real quick. No moles, or no more moles, no additional moles of reactant or product were added. You're just adding water, and so it just dilutes the original tablet a little bit, but that's it. It doesn't change the quantities of anything that you have. All right, part G is a KSP problem. So let's just flip over and see how gravimetric analysis can relate to KSP. We've got a student in another lab wants to determine the iodide content, the Ki, but does not have access to the lead-2 nitrate. But the student does have access to silver nitrate. Notice it's the same molarity. It produces AgIS. The value of KSP for silver iodide is 8.5 10 to the minus 17. Question 1, will this substitution result in precipitation? Yes, because KSP is less than 1. That's really your justification. This is insoluble. It is insoluble. You could also go through a more complicated way to solve this, and that's finding Q. And you'll find that Q here is greater than KSP, so that will shift to the left and precipitate. But that's a lot more work to find Q, because you got to convert your moles of iodide into molarity of iodide, and then you got to plug in that times 0.2 for the Q expression. It's a little more work. It's not a lot of work, but this is all you need. Number 2, the student only has access to 1 Ki tablet and a balance that can measure to the nearest 0.01. Will the student be able to determine the mass to 3 sig figs? So this is directly a sig fig question. So if you can only go to 0.01, the answer is no, you can't get 3 sig figs. Because when you subtract your mass, referring back to part, let's see, what part was it? Part D. In part D, the mass difference is 0. So that only leaves 2 sig figs. All right, so that's 2014 question. Now, that problem was gravimetric analysis, but it wasn't a deep gravimetric analysis. So I pulled out question 2008 because it is a more gravimetric analysis, a more traditional one. And it's very similar. This is still coming up with a precipitate and filtering it, and then heating and drying, all that good stuff. But this time we're dealing with a hydrate. And if you were in my class for pre-AP, you may remember we did an experiment where we did the empirical formula of a hydrate from heating it in a crucible. It was a blue copper 2 sulfate, and then we picked either a green or purple unknown, and your job was to find N. And so that's a nice flashback for some of you. Explain why the student can correctly conclude that the hydrate was heated to a sufficient number of times in the experiment. You see some echoes of the previous problem there? I hope you do, because it was in that exact same problem we did from 2014. We're looking for consistency. No more change in mass. You heat it, the mass is constant, we're done. Use the data above to calculate the total number of moles of water lost when the sample is heated. Total number of moles of water lost. So again, gravimetric analysis can't tell us about moles. It can tell us about mass. So we know what's going on here. We've got 23.977 grams. And the original mass of the empty container, it could be a piece of filter paper, maybe it's a weigh boat, we don't know. But the original container was 23.977, and so we drove off 1.848 grams. grams of water. That's what all that means. So we're just going to convert that to moles. I know everyone can do that. That comes out to be 0.1026 moles of water. Determine the formula of the hydrated compound. Okay, so in part 2 here we got a little bit more work, because if we're going to find the formula, we got to take the moles of water in ratio to the moles of the, in this case, magnesium chloride. So what we've got to do is figure out the mass of the magnesium chloride. So let's go back to our mass of sample, 23.977. Let's go back to part A here. I did something stupid. I was getting in too big a hurry here and said the wrong thing, even though I did it right. Or this work is right. Alright, so I said I subtracted the mass of sample and the container after the third heating. That's right. But what I meant to grab was this initial mass of sample and the container. So 25.825. I was getting ahead of myself a little bit. So that minus 23.977, that shows the amount of water we drove off. So empty plus the hydrate, do the experiment, you drive the water off, and so this is going to be container plus the dry compound. So this is the water driven off. Alright, so now back to part 2. This is container plus dry, and so we're going to subtract from that the container, 22.347. So that is 1.630 grams of MgCl2. We call that the anhydrate, without water. Alright, so I know I'm just jumping all over the place here, but I'm going to convert that to moles down here to save a little space. All of our ratios have to be mole ratios. Molar mass, I pulled this from the key here, 1 mole of MgCl2. And so that means the moles is 0.01712 moles of MgCl2. Alright, now we're going to take a back to the future trip into pre-AP, and we need to find the mole ratio, in other words the empirical formula, between the moles of the anhydrate and the moles of the water. So if you remember, what we would do is that we would take these and divide them by the smallest number, which is 0.01712. And so that would come out to be 1. And that's the coefficient of my anhydrate. So notice there's a 1 in front of MgCl2. And then we do the same thing for the water, and that comes out to be 6. It's like 5.99 something. So there is our N. N equals 6. Our formula is MgCl2 6 waters, magnesium chloride hexahydrate. So that's a little bit involved. It's a little bit of gravimetric analysis, and then it's some stoichiometry, a lot of conservation of mass, and then we do an empirical formula calculation. Part C, a different student heats the hydrate in an uncovered crucible and some of the solid spatters out. This spatter will have what effect? So these are very common questions now. Error analysis. Well, think about it. If you spatter out some extra solid, you don't know. All you know is that the final mass is lower. So you're going to attribute all of that missing mass to water. So you're going to have an erroneously high water loss calculated. And so your empirical formula will be N will be much bigger than 6 because you're just attributing way too much of that lost mass to the water. Alright, and then in the second experiment, the student is given 2.94 grams of a mixture containing these two salts to determine the percentage of mass of magnesium chloride. The student uses silver nitrate to precipitate it. So this is an important part here. Starting with a 2.94 gram sample of mixture dissolved in water. So you've got essentially here a beaker or flask. I just drew a flask with the stuff in it. Okay, so this is going to be your mixture. Describe the next steps to quantitatively, with numbers, determine the mass of silver precipitate. And we just saw this a few minutes ago. I'm going to bring it back just to show you. I even underlined it a while ago. The filtering process. Filtered, washed, dried. Those are your big 3 steps when you filter something. So we do the reaction, and so I'll just kind of come over here. So we need to add the silver nitrate, so that's the reaction. You get your precipitate. And then so 2, you filter it. And I hope you all remember doing a filtration in pre-AP. You filter it, and then what most students usually miss is you got to wash it. All right, so then we wash it, and the purpose of washing a filtrate is just like so maybe there's some of the soluble salts that just kind of got caught up in through some intermolecular forces or whatever. So if you wash it with distilled water, that just makes that stuff dissolve and hopefully go on through the filter paper and go away. And then finally, drying it. Everyone kind of knows to dry it. That takes us back up to here. Okay, we dry it to get rid of all the water so that we know the mass. And those are your big steps. Filter, wash, dry. And then part E, the student determines the mass of silver chloride precipitate to be 5.48 grams. On the basis of this information, calculate each of the following. All right, so in part 1, the number of moles of magnesium chloride in the original. So this is just one giant stoichiometry conversion. So we're going to start with our silver chloride precipitate. We're going to convert it to moles. Okay, and that is 0.0382 moles. And then from there, we're just going to convert that into chloride. So this is AgCl. Moles of chloride using the ratio 1:1. So that's a compound stoich. That's the number of chlorides inside the formula AgCl. And then what I'm going to do is say, okay, well, how many chlorides are in 1 mole of magnesium chloride? And so that's a 1:2 ratio. And what that'll give us is the number of moles of magnesium chloride. So we just did big conversions from grams of AgCl all the way to moles of MgCl2. And then part 2, the final thing here says the percent of mass of MgCl2 in the original mixture. So we need to convert this 0.0191 moles. So I'm tired of doing conversions. 95.2 grams per mole. That comes out to be 1.82 grams of MgCl2. Okay, so let me refer you to the problem statement. There was 2.94 grams originally. So we're just going to convert that into a percent, 61.9%. So that's gravimetric analysis. The lab procedure is pretty much filtration. And so we're just using the change in mass. You just got to be careful as you read your charts, understand what each of these lines means, and just subtract to get the mass of what you're looking for. If it's a precipitate or a hydrate, it doesn't matter. It's just change in mass. All right, well, if you have any questions on that, let me know.